Hey guys, hello everyone. Welcome to Rasayan Academy once again. So today we are going to start the main group elements, and first of all we are going to start with the group 1, that is the alkali metals. Okay. So what are we going to talk about in the main group series? We are going to talk about the important concepts, that is the advanced concept, and going to revise a little bit of the basic also. Okay. So we are starting with the very basic periodic trends, okay, of ionization energy and all of the basic things for alkali metals, and then we move on to the advanced concept, that is crown ethers, cryptands, all of those. Okay, so yeah, let's get started. First of all, we start with very simple flame colors. Okay, so you know already that the alkali metals, that is the first group of the S block right over here, it shows some characteristic colors when they are burnt in the flame. All right, let's say their chloride salts are burnt in the flame. Okay, so lithium is going to give you crimson red color. Sodium is going to give you yellow color. Potassium gives you red to violet, and naturally it is known as lilac color. Rubidium gives you violet color. Cesium gives you blue color. Why do they give you colors? Because when the electrons are excited, they gain some energy in the flame, and when they revert back, they are going to give you the emission spectrum. So basically it is because of the emission spectrum that you get the colors. Now we are going to move onwards and see the thing that we have already discussed, that is the properties, but we are going to study the property individually for the alkali metals. So as you can see, first property is the ionization energy in kilojoule per mole. So as you can see, lithium has 520 kilojoule per mole, and we are talking about the first ionization energy. So if we are talking about first ionization energy, you know that the elements are going to have, the first group elements are going to naturally have ns1 electronic configuration. For lithium, since it is there in the second period, क्योंकि इससे ऊपर क्या है, hydrogen है. So for this one, we are going to have 2s1, then 3s1, 4s1, 5s1 for rubidium. For cesium, it's going to be 6s1, 7s1 for francium, right? So for lithium, it is going to be 2s1. When removing a 2s1 electron, since it is a very small orbital, that's why it's very closer to nucleus, hence maximum energy is required. As we move down the group, the size of the orbital or the shell increases, and that is why the distance from nucleus also increases, so the nuclear pull decreases and the ionization enthalpy also decreases. So as we go down the group, because of increasing size, all of this is going to be like this, right? We usually study the trends until cesium only. Francium being radioactive, very less chemical and physical properties are observed. So yeah, we can ignore the last one. Also, for electron affinity, they have very low electron affinity, because also the electron affinity is positive, as you can see. They don't want to take an electron, they want to give an electron. That's why the electron affinity is positive over here. Okay, all of these are positive. Melting point and boiling point, they give you an idea about the metal-metal bond present in the element itself. So for a lithium element, the metal-metal bonds are very strong, because this mostly depends on the size. Only the size factor dominates over here. That is, smaller the size, better is the packing, right? Let's say this is our metallic lattice. All right, so smaller size is going to give you better packing, and when the size increases, there are going to be greater voids and the packing decreases. So hence the melting point and the boiling point decrease. All right, now we move onwards to electronegativity. Who is the most electropositive element? Cesium is going to be the most electropositive element in the whole periodic table. Okay. Now also, when we move on to the reduction potential, what is this? This is reduction potential. You see, reduction potential is the ability or the ease by which it is getting reduced. Any element is getting reduced. So I want to convert lithium plus to lithium by giving it an electron. Now, what voltage is required for that? That is going to be reduction potential. But you see, for lithium, you have the most negative reduction potential. Why? Because lithium does not want to be reduced. it wants to be oxidized to gain a, helium noble gas configuration. If it loses an electron from over here, it goes to helium. So lithium plus has achieved the duplet. It's very stable. It does not want to be going, it does not want to go back to lithium. Hence, most negative reduction potential. See, all of these are having negative reduction potentials because all of them want to give this one electron away and achieve the previous noble gas configuration. Alright, so alkali metals will have the most negative reduction potential. Right, these are just basic properties. Now we move onwards and take some important names over here. What are these important names? Minerals and ores where these elements are found in nature. Okay. So lithium is found in the form of spodumene. Alright, LiAlSiO3 whole twice, that is lithium aluminium silicate. Okay, this is how lithium is found. Sodium is found in the form of cryolite and obviously in the sea, sodium chloride also. For potassium, it is found as potash K2SO4, carnallite KMgCl3.6H2O. Okay, carnallite being more popular, right? For rubidium, lepidolite. You must have heard these names when you were studying metallurgy in class 12 or IIT JEE. So these are the same thing. Now lepidolite has many options, potassium, and along with potassium there is one more metal which is either of these. It can be lithium also, aluminium, rubidium, any of these. Then we have aluminium silicate present like this and fluorine or OH present as a anion. So the structure is a little bit complex, but yeah, because it has a lot of choices. So calcium and magnesium, most common ore is dolomite, calcium magnesium carbonate, and you have worked with this in your lab also. Barium is present as barite, sulfate salt. Beryllium is present as beryl, that is beryllium aluminium silicate. Okay. Strontium is present as celestine, strontium sulfate. So these are some common mineral and ores in which these elements are found. Okay. Now we move onwards, and yeah, I've already told you the flame test. So these are the colors for the alkali metals. I have combined the alkaline earth metals over here also just for comparison. So both beryllium and magnesium are colorless. Basically, magnesium burns with a white flame. Okay, not exactly colorless, but a white flame. Then calcium, brick red. Strontium is again crimson, and barium is a different color. It is apple green color. All right, it's a light green color. So these are just written together for comparison. Now we move onwards. Now comes the very important topic, that is reducing property of alkali metals in ammonia solution. Okay, so this is very important topic because there has been many questions, previous year question in both CSIR NET and GATE on this. So what is the property? The alkali metals dissolve in liquid ammonia and other donor solvents such as aliphatic amine, for example NR3, in which R can be alkyl, and one more, hexamethyl phosphoramide. This is also important because you don't usually talk about this. P double bond O NMe2 whole thrice. So what is the structure of hexamethyl triamine? Basically it is known as hexamethyl phosphoramide. See, in this, in like this. So this is like an amide only because if I put a carbon over here, it will become amide. So that's why it's a phosphoramide. And phosphorus can have maximum 5 valency. That's why 3 of these groups. So this is again polar. All of these, liquid ammonia, aliphatic amine, and hexamethyl phosphoramide, all of these can give you the same electron capture process of alkali metals. So they give you blue solutions believed to contain solvated electrons. Alright, very important. Now the reaction goes like this. Let's say I've taken sodium metal and dissolved it into ammonia. So it is going to take X moles of ammonia and the sodium metal becomes sodium ion and loses one electron. Now sodium is separately going to be solvated, ammoniated, and the electron is separately ammoniated. Now this electron is actually giving you the blue color. Okay, ammoniated, see we write usually aqueous because here it is ammonia, so we are going to write ammoniacal. So sodium ion ammoniacal plus electron plus ammonia liquid. It is going to react with one of the ammonia molecules which is the surrounding sodium. That electron, when it is reacting with ammonia, is going to give you an amide. Okay, since the electron is like this, definitely it is not solvated in this way. It is not going to be solvated in this way. Why? Because electron and lone pair of nitrogen is going to repel. So how is it going to be solvated? It is going to be surrounded by the hydrogen cage, isn't it? Like this, surrounded by the hydrogen cage. Okay, surrounding completely. Now this electron is going to react with hydrogen like this. One of the bond can open up, another bond goes like this. So what will happen? This hydrogen becomes a complete hydrogen atom, and it can react with another hydrogen atom to give you hydrogen gas like this. And the ammonia is actually left with NH2 minus in this way. It becomes an amide like this, NaNH2. Alright, so this process will give you evolution of hydrogen gas. Okay, evolution of hydrogen gas and this amide. Okay, now one more important point. At high concentration, the solution acquires a bronze metallic luster. So what is a metallic luster? It is a metallic shine that you get on a metallic surface, and a conductivity comparable to the molten metal. How high conductivity? How are we getting this high conductivity? Because at high concentration, we are getting a lot of electrons, like a sea of electrons that we get in the metal. Dilute solutions are paramagnetic in nature. Why paramagnetic? Because there is a free electron. So that's why, because of these electron, it is paramagnetic, corresponding to one solvated electron per metal atom. This paramagnetism decreases at higher concentrations. Why? Because at higher concentration, they are going to be behaving as a conductor. Alright. Now, solution of alkali metal in liquid ammonia are excellent reducing agents. They are used both in organic and inorganic chemistry for reduction. Chalo example dekhte hain. First example, I have just taken a alkyne over here. So if it is a terminal alkyne, it is going to lose a proton, lose a hydrogen actually to give you hydrogen gas, and itself become the acetylide like this. If it is a non-terminal alkyne like this, then it is going to be giving you reduction. And by reduction, I mean it is going to give you the trans product. It is going to be a trans product like this. Okay, you already know about Birch reduction. Yes, uses the same sodium and liquid ammonia. Second example, if I take ammonium ion, that is going to lose the extra proton from over here because electron directly attacks hydrogen. And ammonia and hydrogen gas you are going to get. Similarly, if I take a S8 ring system, that is a crown ring system, and do the same reduction, it is going to give you sulfide like this. If I take organometallic compound, iron pentacarbonyl, how many electron does it have? See guys, iron pentacarbonyl, now you have all studied organometallics, has 8 plus 10, 18 electrons. So it already has 18 electrons. It does not want any more electron, but we are still giving it. So what is it going to do? It will have to eliminate one of the carbonyl ligands and get the electron density like this, and still it is going to be 18 electron system. Okay, so this is how it reacts. Next, metal plus ammonia gives you metal amide plus hydrogen gas. Alright, these are some very common examples. Let's take few more. एक और example है very important. That is, here you see this is going to be nickel tetracyanate cyanide complex. Okay, it has a 2 minus charge. When it gets 2k plus and 2 electrons, what do you get? See here, the oxidation state of nickel is going to be +2. Alright, so what can I expect next? I see after getting 2 electrons, it is going from what oxidation state? Plus 2 atom plus electron atom to finally give you this complex. Alright, so looks like a carbide complex, but this is much bigger. Okay, carbon, the graphene, the graphite structure having negative charge. Then again C60 balls plus 3 rubidium plus 3 electrons gives you Rb whole 3 C60. This one solvated, S for solvated, because there are going to be ammonia surrounding the metal. So this is how the reactions can proceed for different systems. So here we talk about the most important topic of the alkali metals, that is from where the most maximum amount of questions are asked, that is the crown ethers and cryptands. Why do we have crown ethers and cryptands? These are basically some groups, some large molecules which behave as chelating agents. So why do we need chelation? We can need chelation for various purposes. Alright, so these are all chelating agents. We can need chelation for removal of the alkali metals. We can also use chelation for introduction of alkali metals into some reaction mixture, many uses. They can also be used as phase transfer catalysts. Alright, so yeah, most of the times these are used as a phase transfer catalyst. Alright, what is the phase transfer catalyst? Let's say there's a reaction taking place in the organic layer. This is my organic layer and I want to add sodium fluoride. How am I going to add sodium fluoride? This is our aqueous layer. Okay, so in the aqueous layer, I add sodium fluoride. This fluoride is not going to go directly into the organic layer. So what am I going to do? I'm going to take this kind of a crown ether system, which is going to grab sodium along with it. And along with the sodium positive charge, the fluoride F minus is also going to travel inside. So that F minus travels inside the organic layer. So phase transfer from aqueous to organic takes place along with the help of these crown ethers or cryptands. Now questions are asked like this, that which cryptand or which crown ether is going to be best suitable for let's say combining lithium plus potassium plus sodium plus. So you just have to remember that a little bit. Now first one is 18 crown 6. You know, drawing them is super easy. What is written? 18 crown 6. So there are going to be total of 18 atoms in which there are 6 oxygen atoms. This is the way of writing. Okay. Let's say I am telling you I want to write 15 crown 5. I want to write this. What am I going to do? I'm just going to draw 5 oxygen atoms and then I'm going to add them all with this ethyl group. This is going to be 15 crown 5 like this. Okay, how is it going to be 12 crown 4? 12 crown 4 like this. This is going to be very small. How is it going to be 18 crown 6? You just have to draw 6 oxygen atoms like this. In a hexagon, draw the 6 oxygen atoms, connect by the ethylene bridges. This is 18 crown 6, just that. Okay, this is the largest of the crown ether. What is a cryptand? Cryptand is another three-dimensional chelating agent, you can say. That is, it not only has 2 chains, it has 3 chains. That is, if let's say there is a M positive metal, it is going to chelate with these 2 nitrogens, then these oxygen in one chain, another set of oxygen in the other chain, and another set of oxygen in the other chain. So basically the metal is encapsulated on all the sides, okay, in a three-dimensional system. Now, how do we understand cryptands naming? That we will discuss in the next, these diagrams. This is a metal ion encased in a cryptand. ये देखो metal ion encased in a cryptand. कि how the metal ion is going to be put into the cavity of the cryptand. Last is metallar crown. What is this metallar crown? When we have metals and these metals are going to be iron and nitrogen. So basically iron is used in forming the skeleton of this crown ether. So that's why it is known as a metallar crown. Okay, nothing else. Then here also you are just going to use a oxygen chelating agent for some M plus metal. Same thing. Now, what does it depend on? ये देखो, it depends on the binding property of these crown ethers or cryptons. They will depend on the size. Binding property depends on size of the cavity and the radius of the metal So what do you see when I'm talking about 12 ground 4? This is best suited for lithium plus. In this way, when I'm talking about 15 ground 5, it is best suited for sodium plus. When I'm talking about 18 crown 6, alright, so when the cavity size increases of the crown ether, we can accommodate a larger alkali metal ion over there as well. So these are the preferences of these metal ions into the crown ether system. Now we move onwards to cryptands. What are cryptands? You've seen already there are going to be 3 chains. How are we going to name them? Dekho, C221. 221 means 2 oxygen in one chain, 1 oxygen and 1 oxygen in the rest of 2 chains. So what are we writing? We are writing bridging heteroatoms. Okay, we are writing bridging heteroatoms. 2 oxygen, 1 oxygen, 1 oxygen. This is smaller. So the cavity size is also going to be small. Moving onwards, C221. 2 oxygen and 1 oxygen in the ring. 2, 2 and 1. This is how it is. Cavity size a little bit bigger. C triple 2. That is everywhere there is going to be 2, 2. Okay. Cavity size further increases. Now when I've taken C322, then what will happen? 1, 2, 3 will happen, and then 2 in this ring, 2 in this ring. So basically, now see alkali metal ions or radius. There has been question in your GATE and CSIR NET exam like this, that which or let's say what is the cryptand binding capacity for these metal lithium, sodium, potassium, rubidium and cesium. When we are talking about C221, you know that the radius is small. So the best choice is going to be lithium. For C221110, this is the cavity radius and the cavity radius should be similar to the metal radius. So ये देखो ये 80 था, this is 7.58, 110, so it is 8.84, 140, 7.21. So basically these are picometers, smaller radius. So this is how it is going to be for C222 potassium. Alright, so this is how it is 222. This is for potassium. Okay, so बहुत easy concept था, nothing huge about it. Just remember the cavity and the size of the radius, size of the atom. Question: 12 crown 4 binds with the alkali metal ion in the following order. Alright, why is that happening? It is due to lithium plus being very much more reactive to 12 crown 4. Why is that so? Then comes sodium, then potassium, then cesium. 12 crown 4 I have just drawn over here. This is 12 crown 4. Why only lithium? Why not the others? Because lithium fits perfectly into its cavity. Okay, and hence the answer should be right size of the cation. चेंज इन एंट्रोपी बीइंग पॉजिटिव से कोई मतलब नहीं, कॉन्फर्मेशन फ्लेक्सिबिलिटी नहीं चाहिए, हाइड्रोफोबिसिटी नहीं चाहिए. वी ओनली नीडेड दिस 12 round 4. Now we are going to move onwards, right? Yes, it's a very beautiful question, guys. The formation constant of the complexation of M plus all these alkali metal elements with cryptand C222 follows the order. So you know about the cavity size, you have just seen the table. You're not supposed to like remember each of these values, but you just remember C222 fits K plus the best because it is the best size according to it. So K plus is going to attach better, then sodium, then cesium, and lithium plus is very small. It will right pass through it. So this is going to be the correct answer. K plus minimum is wrong. Cesium plus is big and sodium is again small. So see, this is the table right over here. C222 perfect for K plus. Rubidium and cesium are like this. Cesium plus is again small. Just go through this, you will know that. Just remember for C211 lithium is best, C221 this is best, C222 this is best, C322 this is best. That's all. Next, we are going to also see an example of another type of macrocyclic compound. Macrocycles and related ligands form the most stable complexes. Okay, so one example is valinomycin. What is valinomycin? The naturally occurring molecule valinomycin is an antibiotic that selectively coordinates K potassium. The resulting hydrophobic 1:1 complex transports potassium through a bacterial cell membrane, depolarizing the ion differential and resulting in the cell death. So, this is nothing but a carrier of potassium. See, this is how it is going to interact with potassium through the oxygen and mostly the nitrogen group. Oxygen is bound, mostly the nitrogen group. Okay, yeah, we call them ionophores. What are ionophores? Ionophores are some organic molecules which are present in our system and in the nature where the inner, the inner side of a compound is basically ionic. This side is going to be ionic, but the outer side is going to be hydrophobic. This way, these kind of molecules can carry the ions, the metal ions, through the ion, cell membrane without consuming energy. So ionophores are used for passive transport. That is, without conducting, without taking up a lot of energy, they are just going to carry the metal ion right through the cell membrane. Okay. Another important question, guys. ये देखो. The correct order of the retention of cations on a sulfonated cation exchange resin column is. So I think that I've already given you an idea about this. What is a sulfonated cation exchange resin column? You are having the same column again. There's a tap like this. The water is going to come out drop by drop. Now the resin is sulfonated, that is it has a acidic group RSO3 minus. This negative group is going to attach with the metal plus and it is going to you know stick all the alkali metals to it, or it is going to pass away all of them. See what happens is, let's say I have taken heavy water. Heavy water means it is having a mixture of salt. I want to remove that salt and purify the water. So I will add that water from over here. All of the metal ions are going to stick to the sulfonate and pure water is going to come out because the alkali metal ions are connected. Alkali ho or any other metal ions will stick to the sulfonated system. Now, when I want to clean this once again, when I want to clean the resin once again, I will use clean water and pour it over here, or let's say I'll use acidic water H plus and pour it over the mixture, because then all of the metal ions are again replaced by H plus RSO3H. It becomes plus minus like this. Okay, so that is going to be again neutralized. So what happens now when I'm taking H plus and neutralizing this system, all the alkali metal ions are going to come out. जो पहले फंस गए थे water purification में, those are going to all come out. Now, what is the correct order of retention? Retention means पहले कौन आ रहा है? Which one is going to come out first? Or that is elution. Yeah, that is actually elution. Comes out first. Retention मतलब कि stays connected या stays back, that is retention. So let me tell you, we have talked about this while we are talking about the hydration radius. Who has the maximum hydration radius? Lithium plus has the maximum hydration radius. Okay, and that is why it is going to least interact with the sulfonate and come out quickly. So lithium plus is going to come out quickly. ये हम लिख रहे हैं elution का rate, the rate of elution. Then comes sodium plus, then comes potassium plus. This is the rate of elution. What is going to be the rate of retention? Just the opposite. Retention. मतलब कि the one which is sticking to the resin for a longer period of time because of better interaction. कौन रुकेगा? K plus, sodium plus and lithium plus. Alright, all of these in the alkali metal. What about this silver plus? Silver plus is a D block element. Okay, and it is going to be having a noble gas configuration, hence it is going to come first. इसका retention सबसे ज़्यादा होगा, maximum retention, because also of the covalency. Covalent character, more stronger bond forms between the sulfonic acid and silver as compared to potassium, sodium and lithium. So A is going to be the correct answer. Okay, very beautiful application. Now also, since you don't get confused in future, I'll tell you 4 different types of ion exchange resin which are used in chemistry and along with their functional groups. Strongly acidic cation, typically featuring sulfonic acid. See, alright, so these are highly, strongly acidic, also negative. Example is sodium polystyrene sulfonate. Okay, this is an example of sulfonated resin and often used for water softening and demineralization operations. Okay, just now we have seen water softening. Strongly basic anion, typically featuring quaternary amino acid. For example, trimethyl ammonium group. Example, poly-APT, APT-AC. Alright, you just can remember trimethyl ammonium group. That will be all. Good for silica, uranium and nitrates removal. Weakly acidic cation, typically featuring carboxylic acid group, an ideal choice for dealkalization part and also for softening streams with high salinity levels. Okay, मतलब कि क्या हुआ? Alright. So where you are having a lot of, let's say, sodium or magnesium 2 plus in water, what can we do is we can take any group which has a negative charge over here so that it can stick the positive metal ions, so that you can get more cleanliness in the water. Weakly basic anion, typically featuring primary, secondary and tertiary amino groups. Example, polyethylene amine are effective for demineralization where removal of SiO2 and CO2 are not required. Also effective for acid absorption. So when we are using the amino group, then there's a different process. Definitely all of these will have different process, but these are using an amino group or a polyethylene amine basically gives you a soft medium, not a very highly strong medium, strong bases. All of these are strong bases which are having negative charge, but this one is a weak base and hence weak basic anion. Okay. Alright guys, so it's now time to move on to some reaction part of the main group elements. Now, first thing guys, there are a lot of reactions which you can go through, but those reactions are covered mostly in the basic classes, or let's say in the lower levels, IIT JEE level, IIT JAM level. When we move onwards to CSIR NET level, a little bit of those reactions are asked, and mostly the target is on the concept. Okay, so I'm just giving you a little idea about, you already have notes of all of these things, and because you have all studied this in class 11, 12, and your BSc level examination. So yeah, we are just going to do a quick revision. So you all know that if these elements are going to form oxides, superoxides and hydroxides, what are going to be their behavior? So lithium being the smallest, lithium, sodium, potassium, all those, so size increases when we move down the group. So what happens is, about the oxide anion, the superoxide anion, as well as the peroxide anion. So yeah, this one is peroxide, and superoxide is going to be a little bit bigger, right? So the size is going to be increasing for these two and very small for this one. So the smaller elements like lithium is going to naturally form a simple oxide like this. Okay. However, when oxygen reacts with sodium, it naturally forms peroxide. Why? Because the size of peroxide is a little bit bigger. All right, Na2O2. So this is going to be O2, 2 minus. This is your peroxide. Okay. And what does the structure of the peroxide look like? It's basically OO minus, like this. It's also known as an open book open book structure. So just go through it once. Now we move onwards and go directly down to cesium, because it's going to be very large. So when it reacts with oxygen, naturally it is going to form the superoxide. Okay. What is a superoxide? That is one negative charge shared by two oxygen atoms. Okay, and you have also studied the molecular orbital diagram of dioxygen. You know that when we go on adding one electron into the antibonding pi star orbital, the bond order decreases. Okay, so for a dioxygen atom, the bond order is going to be 2. When I add one electron to this, it is going to become O2 minus, that is your superoxide. The bond order is going to be 1.5. When I add one more electron to this, it is going to form O2 2 minus, that is peroxide. So bond order is going to be 1. Okay. So the same thing is followed over here. Now, when we take pure lithium oxide, okay, LiO2, so this is superoxide, which we have to like make in some different settings, some different conditions. Then it is going to decompose into lithium peroxide, and at 450 degrees centigrade, it is going to finally form your stable dilithium oxide, plus half of oxygen is released. So this is going to be stable for lithium. But for sodium, the peroxide is more stable because of the size, and for the bigger size elements like cesium, it is going to be again superoxide. Now, what happens when I am taking magnesium? Let's say this is a reaction of the alkaline earth metal, but just for discussion, if I take magnesium with dioxygen, it is going to form simple oxide, and with nitrogen, it is going to again form the nitride. Why am I showing this to you? Because this is showing diagonal relationship with lithium. So lithium and magnesium will show same reaction with both oxygen and nitrogen. Okay, just star mark this one, right? And this reaction is also same for lithium and magnesium. See, carbonate CO3 2 minus, this is a large anion. Okay, so when magnesium carbonate, or let's say lithium carbonate, has formed, we are heating it because the lattice is not very strong because of the size difference. What happens then? It is going to break down to again give you the same thing, simple lithium oxide and carbon dioxide. Okay, so this is how it works for both magnesium and lithium. They are showing similar properties, so hence the diagonal relationship. Moving onwards to what happens when we are reacting sodium hydroxide with sodium. Okay, why this peculiar reaction? Because we now want to form an oxide, that is Na2O. This is, we don't naturally get it from the reaction of sodium and oxygen. That's why if we want to make this, we can make it with this method. Okay, the natural oxide of sodium is going to be peroxide. So this is another reaction in which you can form simple oxide of sodium and hydrogen is removed. All right. So, this is just an example of showing you that if we want to make the simple oxide, we can do so, but the process is going to be different. And we can do the same thing for cesium also, but the process is going to be different and it is going to be less stable because cesium is very big in size. Okay, so more of these reactions you can go through in your any of your textbook. It is very simple. Now, some important points of the group 1 element. See, this is like a very simple notes. I've already made notes of this. You just have to note it down. The color of lithium oxide and sodium oxide is pure white. Okay, both of these are pure white. While K2O is pale yellow, light yellow. Rubidium oxide is bright yellow. Cesium oxide is orange. And this is what we are talking about, normal oxides. These are all normal oxides. All of them have anti-fluoride structure. Okay, so you remember what is anti-fluoride structure? This is absolutely opposite of CaF2. Just remember both of these structures. We have studied this in solid state also. Anions are going to be adding in the tetrahedral cation form, which is just opposite of CaF2, except CS2O, which has the CdCl2 layer structure. So this is a BCC structure, you all know that. Okay. Now moving onwards, simple reactions. Lithium oxide, when dissolved in water, is going to give you a base. That is how the basic property of the oxide, metal oxides are shown. Okay, sodium oxide reacting with water gives you sodium hydroxide. Potassium oxide reacting with water gives you potassium hydroxide. Okay. Also, metals directly react with water to liberate hydrogen. This property also that only all the alkali metals are going to react with water to give you hydrogen gas. That's why on YouTube you see a lot of people throwing lithium, big stones of lithium, sodium directly into the river. Don't attempt that, okay? Because definitely you will have a blast to enjoy, but that makes the water very too much alkaline. Now, lithium directly reacts with water, gives you LiOH. Now, this is a slow reaction, okay? Next, sodium, when reacts with water, shows a vigorous reaction. But if we go down, down, down into the same alkali elements group, the reaction becomes very much violent. Why is that so? Why potassium is more violent than sodium? I think all of them should react equally. No, lithium is the smallest. It is very small. That's why a little bit less reactive than sodium. Potassium is still bigger. So it is very, happy to react as compared to sodium. And as you go down, if you have cesium, it is going to be very high energy reaction. Okay. So just remember this point. It is also very important. Solubilities of hydroxides are good for all except lithium hydroxide due to covalency. And it's not just lithium hydroxide, it is going to be any salt of lithium is going to be less soluble than all the other alkali metals. Why? Because of the covalency factor, because lithium plus has a very small size, and according to Fajan's rule, you already know that the nuclear charge matters. That's why lithium plus has very high polarizing power. It can polarize the anion very nicely, so covalency arises. Next, so we are having sodium peroxide. If we dissolve this in water, we are going to get NaOH base plus H2O2. That is our peroxide, hydrogen peroxide. Now, Na2O2 is pale yellow. It is used in bleaching, wood pulp, paper, and fabrics. Okay, so this is a very important use. You must remember this at least once. Now, what happens is it is also used in metallurgy. How? Let's see. So when if you have studied the metallurgy of aluminium, how aluminium is extracted, you will know that from a slag, or let's say from many impurities, the aluminium has to be extracted out. How is that going to happen? From all the soil, silica, everything. See, this is all, everything is there in this. There is silica, there is iron, there is aluminium, everything is there in this. All right. How are you going to separate only aluminium from this mixture? You can very cleverly put Na2O2 plus H2O into this mixture. What will happen? It will form Na2O2 and H2O is going to form NaOH. Or you can directly also put NaOH into this, because NaOH and aluminium are going to form sodium aluminate, and that is going to be dissolved, because ये क्या होता है, this is water soluble, it is going to be dissolved with this and it is going to be eliminated, only aluminium. So it is a very important step in the extraction of aluminium. Okay, now one more thing, why is aluminium able to do this and not the other metals or other elements? Because aluminium is amphoteric in nature, it can react both with acid as well as the base. Okay, next, Na2O2 plus CO gives you sodium carbonate. Very simple. So just remember these few reactions, and definitely there is a lot of scope to study more. तो आप कहीं से भी देख के पढ़ सकते हो. Superoxides are all colored due to paramagnetic O2 minus ion. So all of the superoxides are going to be colored. Now, sodium plus half O2 is going to give you a simple oxide. Na2O plus again half O2 gives you Na2O2. Superoxide. Okay. Sorry, this is peroxide. This is only peroxide. Right. Now, peroxide, when again it is going to react with half of oxygen, then it is going to give you NaO2, because oxygen quantity is more, right? Right. Now, LiO2, that is lithium superoxide, and sodium superoxide are yellow, while potassium superoxide is orange, rubidium is brown, cesium is orange again. Okay. Now, sodium bicarbonate is used as a baking powder. All of these like little uses, extra points. Baking powder for making the cake rise by dissociating into sodium carbonate and CO2. Okay, and one more thing you have to remember, guys. Just now I've shown you that here if I break down, if I just heat this lithium and magnesium carbonate, they are going to give you oxide, but sodium carbonate does not give you oxide, and that is why understanding the thermal property and the solubility is very important. So for the carbonates and the sulfates, the thermal stability increases down the group, because when we are going down, the size of the cation also increases. Anion to bada hai hi. That's why with a bigger cation, the lattice is better. Hence, the stability of the carbonate and sulfate, both of the anions are big. That increases down the group. Okay. Now, group 1 metals form solid bicarbonates. Okay, solid, not liquid, solid. Sodium bicarbonate forms a polymeric infinite chain, while potassium bicarbonate forms a dimer held together by the hydrogen bonds. Okay. All carbonates and bicarbonates of alkali metal are soluble in water. And let me also tell you that for the alkali metals, koi bhi ho, whether it is a nitrate or a chloride or anything, all salts are water soluble. Yes. And when you go into the lab first time, when you are doing the qualitative analysis, first time when you are taught this, it is written in your lab manual in the first page that all the salts of alkali metals are soluble in water. So we remember this. Now, the halides of alkali metals form trihydrates like this, Lix.3H2O, which are formed best by lithium plus, and it decreases down the group. Okay, why does it decrease down the group? Because down the group the size of cation increases, and hence the coordination number also increases. So maybe it's hexahydrates that they are forming. So trihydrates only formed by mostly lithium. Alkali metals form polyhalides. See, very important. What are polyhalides? These are you'll also study this in group 17, because there are many types of polyhalides. There are neutral polyhalides, anionic and cationic polyhalides. Okay, so Potassium iodide, when reacting with I2, forms Ki3 over here, which I3 minus is basically a linear structure. You have been asked this a lot in your CSIR NET exam. Let's say I combine this question and I'm asking you that when iodine reacts with this dash salt, it forms a colorless solution, because you know iodine is violet. It forms a colorless solution in which there are 9 lone pairs. 9 lone pairs. So in that final complex that you're having, there are 9 lone pairs. Would you be able to find out? Absolutely, because here you see that this iodine in the center has 3 lone pairs like this. And these ones, all of these are going to be like this. So 1, 2, 3, 4, 5, 6, 7, 8. How many lone pairs? 3 and 3, 6. 3 more over here. So total 9 lone pairs this is going to have. So definitely you must be forming I3 minus and the compound must be Ki3. Very simple. So you know a question can arise out of thin air. So yes, just be careful. KBr plus ICl, this is going to give you a mixed polyhalite. This is a mixed one. And who is reacting with whom? See here, I is connected with Br and Cl, because you know I is iodine. This is the most electropositive. So most electropositive stays at the center only, like this. Then Kf plus Brf3 will give you KBrF4. This you have also studied in the acid and base concept. Okay, right. The alkali metals react with hydrogen to give ionic hydrides, which on electrolysis liberate H2 on anode. Okay, what is an anode? Anode is negatively charged, cathode is positively charged. So alkali metal react with hydrogen to give you ionic hydrides, which on electrolysis, again breaking down, liberate H2 on the anode. Very famous examples are lithium, aluminium hydride, sodium borohydride. What are these? These are ionic hydrides. Yes, they react with hydrogen directly, the alkali metals. See, this is also an ionic hydride, lithium hydride. If I react this with AlCl3, another salt, then this is also a hydride. But this is mostly aluminium hydride, lithium aluminium hydride, like that. Plus 3LiCl. This is a very popular reducing agent, you know that. Sodium hydride plus BOCH3 whole thrice gives you sodium borohydride plus 3NaOCH3. That is a displacement reaction. So these are just the formation reactions of these very popular compounds that you have used in organic a lot. Okay. Yes. Another important point, see, I told you, just remember some trends. Whose trends? Trends of, let's say, thermal stability, trends of melting boiling points. Thermal stability and melting boiling point are same thing. Lattice energy, hydration energy, solubility product. Okay, see, solubility product, you cannot just find out the K value for all of these. You can't remember that, right? What are you going to do? As we go down the group, the solubility increases, so the solubility product is also going to increase, but not for all, not for each element. Let's say for carbonate, which is a big anion, maybe the lattice is more stable going down the group and maybe the solubility product decreases, so you have to go through all of these variables for the trends. ठीक है, अब जैसे देखते हैं हाइड्रेशन एनर्जी ऑफ alkali earth metals are in kilocalorie per mole. Alkali metals, not alkaline earth metals. Lithium plus minus 121, sodium plus minus 95, K plus minus 76, rubidium plus minus 69, cesium plus is going to be minus 62. So why minus? Because this is the energy which is released out of a system. That's why minus. Okay.